Hello and welcome to the introduction to the VARTM lab theory. I'm Frank Thomas, your TA for this lab for EMCH 362. Our objective for this lab is to study fluid flow through a porous medium. This will be done in the context of a composite infusion using vacuum-assisted resin transfer molding, or VARTM for short. So just as a brief introduction to what is a composite, it's a fabric reinforcement base, either like carbon fiber, glass fiber, other materials such as Kevlar, which provide high tensile strength, but they don't have any real compressive or bending rigidity, so you can't build anything out of it, combined with a polymer matrix, which on its own has lower strength, but it redistributes load to the reinforcement, giving you kind of the best of both worlds. We have kind of an infused woven fabric pictured up top, and then down below you can see like a manufacturing process for like an airplane or something using carbon fiber. So composite manufacturing involves impregnation of a reinforcement so that the matrix is consistent. Gaps that result from poor impregnation are called voids, and they lead to significant strength degradation. So getting a good impregnation is really important. Methods for doing this vary based on what materials you have, what applications you're using it for, and what your budget is. So pre-preg is a pre-impregnated material that produces very high quality parts, but it's also very expensive and generally also requires really expensive curing equipment to get a good part out of it too, such as an autoclave like we have here at the McNair Center. Another process is called wet layup. It's inexpensive compared to other procedures, but part quality is only as good as the person doing it, and you really can't get something on the level of a pre-preg part. It involves actually impregnating the fabric with the resin yourself by kind of pouring it over and rubbing it in and then laying up and then hopefully getting the kind of compression you need to consolidate effectively. Kind of in between that's really popular is VARTM, which is what we are studying today. It creates improved part quality over wet layup, but the cost is nowhere near that of manufacturing with pre-preg. So to define VARTM, VARTM stands for vacuum-assisted resin transfer molding, which we'll break up to kind of figure out what it actually means. So vacuum-assisted stands for the fact that the part is actually held under a vacuum bag as it's being processed and curing. Resin transfer molding refers to the fact that the fabric is first placed in a mold and then the resin is pulled into the mold. So to put that all back together, the resin travels through the fabric in a mold pulled by a vacuum pump, after which point it cures and you have a pretty decent quality part. Here we have a diagram of our VARTM setup. So to just look at each little part of it, first we have our mold, which in our case is an infusion table, which is just a decently thick but well polished tempered glass table. So it's able to withstand a little bit of temperature variation because a lot of resin curing reactions are exothermic. That is true of the resin that we use for this experiment. On top of the infusion table, we have placed against it our fabric preform, which in this case is glass fiber fabric. And around the border of everything is sealant, which in our case is called tacky tape. It's kind of gummy and it holds vacuum fairly well. Coming through this tacky tape barrier is our resin inlet tube. We also could put a port vertically through the bag. That's also very common. It's all in the placement depends on your part and how you want to run your experiment. In our case, putting it directly through the tacky tape onto the part at the very edge is the best solution. On top of our fabric preform, we have peel-ply, which is just a fabric that allows for easy removal of the flow media, which is placed on top of everything. As the fibers in the fabric are relatively dense, they don't have very high porosity and therefore don't allow for much resin flow. But we want the resin to be all the way across the part consistently, so we have the flow media to enable that to happen. And on top we have everything, we have a vacuum bag, and that allows the vacuum pump to apply pressure to the entire part and also prevents air from getting into the curing part, because air bubbles when cured become voids, and voids destroy the mechanical strength of your composite part. Touching the edge of the fabric preform is a breather material, which in our case is just a cotton batting. It's right underneath this base part of the vacuum outlet tube, and so this allows the vacuum pump to apply the pressure. Resin can get in here, we don't want it to, so in our case we'll be stopping the experiment before, but we often have this outlet tube going into a resin trap so that if resin comes out the outlet tube, it won't get into the vacuum pump because that would destroy the pump. So measured quantities for this experiment include the mass of your fabric, as well as the dimensions of the fabric preform, which in our case is just a stack of several layers. We can find, if we know the density of the fabric, so if we multiply the mass by the density, we can find the actual volume of the fabric itself. And knowing that, we can find porosity, because we're also measuring volume. So the measured volume will be much higher than the actual volume of the material. And then once we're running the experiment, we would measure the position of the flow front over time. And that will allow us to find the permeability based on Darcy's law, as well as the steady state volumetric flow rate. So I say steady state because initially the fabric fills relatively quickly and not very consistently. So to find the steady state flow rate, we exclude the initial filling up, and then as the position over time curve becomes more linear, that's where we would find the slope to estimate the flow rate. So here we have the classic version of Darcy's law. It links our volumetric flow rate to our pressure differential, and it's proportionate based on the viscosity of our fluid, the cross-sectional area, and our permeability K. Note this negative sign here. That is based on that is primarily due to the pressure differential. So in our case we have a vacuum, so our pressure differential will be negative, so it will cancel out, giving us a positive flow rate. It's mostly a sign convention. Once we divide out the area term, that gives us a linearized flow rate here, and we've also kind of split off from the area this porosity. It's kind of a normalized term. And we just have a finite distance x and a finite pressure differential here, indicated by the delta instead of an infinitesimally small pressure differential as indicated by the previous letter D. So these effective quantities are what we'll be measuring, its effective permeability. Once we integrate both sides by T, well, we actually need to group the X term to the other side. So we kind of take that off and put it here. And then we integrate both sides. We integrate both sides. So this one by dt. And then we get this final form x squared on the one side and t on the other. So the general idea is that if we have a consistent flow rate, it will be a roughly linear relationship between the time and the square of the distance. And all these other terms are largely the same. So most of these will be known. This is known. This is known. We calculate this. And so if we just plot these quantities, we can use the slope to find our effective permeability. Our effective porosity here is a weighted average based on the height of each layer. So we have the porosity of the fabric. That's 1 minus the fiber volume fraction, as you'll see calculated in the table later on, times the height of the fabric, and the distribution media porosity times the distribution media height, all over the total mold height, H effective. This process is kind of run in reverse to find our individual layer permeabilities. So we have our effective permeability times the total height, and we subtract out the dm permeability times the dm height, and then divide everything by the height of the fabric, and that will give us our individual layer permeability. Another quantity we're looking at is volumetric flow rate. So here we have our generic formulation of it, where we have a consistent motion of a fluid through a consistent cross-sectional area A. And then if we kind of convert it to our effective formulation for our more complex geometry, we have Q effective, and then this dx over dt is here described as U, and then the A becomes the effective porosity, the amount of the area cross-sectionally through which it can travel, multiplied by the width times the height, which is the actual cross-sectional area of the setup. So we find our steady state flow front velocity, that dx over dt, and then we find this. So we find the slope of that linear portion, and that's able to, if we know the porosity and the dimensions which we've already measured, then we can estimate this flow rate. So that gives us units of volume per unit of time. Here we have all the values that you should need in processing your data is given. You'll be given a data set for either 6 or 8 layers. And here we have the measured single layer fabric height. From the number of layers and the layer height, you can calculate the total preform height. In the lab, we would actually measure the height of the preform, but just as an exercise for you to do, you can go do it the other way around. Here's the height of the distribution media as measured, and from your preform height and your distribution media height, you can calculate the effective height. used in calculations. We also have your preform width and length. That corresponds to 2 and 12 inches, though we've already converted it to meters because you always want to do your stuff in base units, and I didn't want to be too mean. So you can calculate the volume from that. We have the measured fabric mass and the density of the glass fiber material itself. So note that for the fabric mass, it changes for 8 layers. That's kind of obvious, but just don't make sure you're using the right number and not just grabbing whatever number you saw first. So from the fiber density and the mass, you can calculate the actual fiber volume, and knowing that, you can find the ratio between the actual fiber volume and the preform volume to find the total fiber volume fraction, and that's subtracted from 1. It will give you your porosity. We've already given you the distribution media porosity. You can do something very similar to find that if you want to do it on your own. Of course, we haven't given you the details on that, but it's not too difficult. And then the effective porosity is what you need to calculate, and that formula has already been given to you. We have the fluid viscosity and pressure differential. Those are known. Note the negative sign. I don't want to see any negative effective permeabilities, or even so if the data is not very good, sometimes you'll get negative single layer permeabilities, but in this case you should not see that. We have made sure that that's not the case. And then we have the distribution media permeability, and that will be used on your calculations as well. Here we have the Excel data used to find to solve one of these problems, to find the effective flow rate permeability and individual layer permeability. So the amount of data you will be given will be position and time data. So you'll need to calculate that x squared. It shouldn't be too hard. And then from that you can find the slope of the linear portion of the position, as well as the slope of the squared position. Here we have plots that will be needed in your lab reports, so these aren't too difficult to make. I've already cut back on the data to the point where it's linear. It's largely linear. If you want it to be really linear, we could cut off maybe these data points here as well, but it just gives a slightly different value for flow rate, and it's not different enough to, we want to make sure we have a sufficient number of data points while ignoring the most nonlinear of them, which would be these here. And then here's our position squared chart. We need that. You need that as well. So having the slope, or having the equation on the graph, is helpful, but what's better for calculation purposes and just to make everything more easy for you to do in Excel, I personally prefer to use a function. So the square slope is using the whole data set, and the linear slope is using just the portions that are already highlighted as seen in the graph. If you just need the slope, the function slope will give that to you as well. But I went ahead and used linest as just so I could see the intercept as well. Ideally, your square slope intercept should approach 0. If it doesn't, then you might have an issue with your data, or however you did it. The linear slope is probably non-zero, because if you kind of extend this trend line, it's hard to see, but it does have a positive a non-zero y-intercept, and that's perfectly normal and to be expected. So we've given you the correct values for the effective flow rate and permeabilities. Those are based on the values in the preceding table and the calculated values that should result from a proper use of the equations that have been given to you. So a good way to check to make sure that your answer or your values that you're putting in your lab report are correct would be to make sure that you can take this data as given and come up with the correct values. So I would strongly recommend making sure that you can do this with the example data given in this slide, and then if you can do that with this example data, you should have no issues doing the same with the actual data that will be given to you. You'll also be given some data sets for both 6 and 8 layers, but that's just going to be effective permeability, effective flow rate, and then individual layer permeability, and you'll be comparing those using statistical tests, but that should be pretty standard. Excel has a built-in t-test function, so you should be able to generate a p-value using that. But if you still have any issues with that, I will answer questions via email, but that should be pretty simple. Thank you for watching this presentation, and if you have any issues or don't understand a concept, please feel free to email me for questions. My email is included on this slide, and I will get back to you in a timely manner. Good luck on the lab reports.